Right now, as you watch this video, there are millions of people gazing up at that rust-coloured dot in our night sky, wondering the same thing our ancestors have wondered for centuries. That distant world we call Mars holds secrets that could fundamentally change everything we thought we knew about life, intelligence, and our place in the cosmic order. Tonight, we're diving into one of the most fascinating questions in all of science. Not whether Mars could have harboured simple microbes or primitive bacteria, but something far more extraordinary. Could an entire civilization have once thrived on the red planet? Could ancient Martian cities have dotted landscapes that are now barren deserts? And if they did exist, what happened to them? Before we embark on this mind-bending journey through space and time, I'd love to know where you're watching from tonight and what draws you to these cosmic mysteries. And if you find yourself captivated by questions that challenge our understanding of the universe, I'd be grateful if you gave this video a like and perhaps subscribe to join our community of interplanetary explorers. Get ready. The journey begins now. The question we're exploring tonight isn't just science fiction speculation. It's rooted in genuine scientific discovery and observation that has been accumulating for decades. Every new Mars mission, every high-resolution photograph, every soil sample analysed brings us closer to understanding the true history of our planetary neighbour. And that history is far more complex and intriguing than most people realise. Picture Mars as it exists today. A frozen desert world with an atmosphere so thin that liquid water instantly boils away. Surface temperatures that plunge to minus 195 degrees Fahrenheit. Radiation levels that would kill any Earth organism in minutes. It's a hostile, seemingly lifeless wasteland that appears incapable of supporting even the most primitive forms of life. But this desolate world we observe today tells only the final chapter of Mars's story. The opening chapters paint a picture so dramatically different that it challenges everything we think we know about planetary evolution and the possibilities for life beyond Earth. Scientists have discovered something remarkable about ancient Mars. Billions of years ago, this world was unrecognizably different from the frozen desert we see today. Evidence suggests that Mars once possessed something that would have made it far more Earth-like than we ever imagined. A thick protective atmosphere, liquid water flowing across its surface in vast rivers and collecting in enormous lakes. Temperatures warm enough to sustain liquid water for millions, perhaps billions of years. The evidence for this ancient Martian paradise comes from multiple sources, each piece of the puzzle independently confirming what seems almost impossible to believe. Orbital spacecraft have photographed vast networks of dried river channels carving through Martian terrain like ghostly fingerprints of ancient waterways. These aren't small streams, but massive river systems that once carried volumes of water comparable to some of Earth's largest rivers. NASA's Mars Reconnaissance Orbiter has identified what appear to be ancient shorelines, the kind of geological features that form where large bodies of water meet land. These shorelines suggest that Mars once hosted lakes so large they could more accurately be called inland seas. Some researchers have even proposed that the northern lowlands of Mars once contained an ocean, covering nearly a third of the planet's surface. The Mars rovers have provided even more compelling evidence from ground level. As they've rolled across the Martian landscape, these robotic explorers have discovered sedimentary rock layers that could only have formed underwater. They've found mineral deposits that require liquid water to create. They've identified chemical signatures in the rocks that tell the story of ancient Martian rivers, lakes, and possibly even hot springs. Perhaps most remarkably, recent analysis of Martian meteorites has revealed evidence of hot water activity on Mars dating back an astounding 4.45 billion years. This pushes the timeline for habitable conditions on Mars back to the very earliest period of the planet's history, suggesting that Mars may have been suitable for life even before Earth became fully habitable. But here's where our story takes a turn that should make every thinking person pause in wonder. If Mars was once a warm, wet world with conditions suitable for life, what kinds of life might have emerged there? And how far might that life have evolved during the hundreds of millions or even billions of years when Mars remained habitable? On Earth, life emerged relatively quickly after conditions became suitable, and it didn't remain simple for long. Within a few billion years, Earth went from sterile rock to a planet teeming with complex organisms. If Mars had similar conditions for similar timeframes, could it have followed a parallel evolutionary path? This is where speculation begins to merge with scientific possibility. While we have no direct evidence of complex life on ancient Mars, we also have no evidence that complex life couldn't have evolved there. The same physical laws, chemical processes, and evolutionary pressures that produced intelligence on Earth would have operated on Mars as well. The idea becomes even more intriguing when we consider recent discoveries about the incredible persistence of life in extreme environments on Earth. Scientists have found thriving ecosystems in the deepest ocean trenches, in boiling hot springs, in acidic lakes, and even in the radioactive zones around nuclear disasters. Life, it seems, is far more adaptable and resilient than we once believed. Could Martian life have been equally adaptable? Could it have evolved not just to survive, but to thrive in conditions we might consider impossible? And if it had millions or billions of years to develop, could it have achieved levels of complexity and intelligence that rival or even exceed what we see on Earth? These questions have captivated not just scientists, but anyone who has ever looked up at Mars and wondered what secrets that distant world might hold. And over the decades, various observers have claimed to find evidence that Mars once hosted not just life, but intelligent life. Civilizations that built structures, altered landscapes, and left behind traces of their existence. The most famous of these claims emerged from a photograph taken by NASA's Viking 1 orbiter in 1976. The image showed what appeared to be an enormous face carved into the Martian surface, complete with eyes, nose, and mouth. The structure was massive, stretching nearly 2 miles from end to end. To many observers, it looked unmistakably artificial, as if some ancient Martian civilization had carved a monument into their planet's bedrock. The face on Mars, as it came to be known, sparked immediate speculation about ancient Martian civilizations. If intelligent beings had once lived on Mars, wouldn't they have left behind monuments, just as ancient civilizations on Earth left behind pyramids, stone heads, and other massive structures? The face seemed to provide exactly the kind of evidence that archaeologists look for when studying ancient civilizations. But the face on Mars was just the beginning. Other observers began identifying additional features that seemed to suggest artificial construction. Geometric patterns in crater formations, straight lines that appeared too regular to be natural. Rock formations that seemed to show architectural details like windows, doorways, and structural supports. The speculation reached fever pitch when some researchers claimed to have identified what appeared to be an entire complex of artificial structures in the region around the face. They pointed to what they interpreted as pyramids, roads, and even the remains of what might once have been a massive city. The area was dubbed the Cydonia region, and it became the focus of intense scrutiny from those convinced that Mars held evidence of ancient intelligence. These claims weren't coming from fringe conspiracy theorists alone. Some legitimate researchers began taking seriously the possibility that Mars might preserve evidence of past civilizations. After all, if conditions on Mars had once been suitable for life, and if life had indeed evolved there, why couldn't it have eventually produced intelligence? The logic seemed sound. Earth's fossil record shows that once life emerges on a planet, it tends to become increasingly complex over time. Given enough time and suitable conditions, that complexity can eventually produce intelligence. If Mars had been habitable for hundreds of millions or billions of years, intelligence might have been an inevitable outcome. Furthermore, Mars offers something that Earth doesn't: superior preservation conditions. Earth's active geology, weather patterns, and biological processes constantly erase traces of the past. Continental drift buries ancient surfaces. Erosion wears away structures. Vegetation grows over ruins. On Earth, even our most impressive ancient monuments are gradually being worn away by natural processes. Mars, by contrast, is geologically quiet. Without active plate tectonics, flowing water, or biological processes to disturb the surface, structures on Mars could potentially survive for millions or even billions of years. If an ancient Martian civilization had built monuments or cities, Mars' current conditions would preserve them far better than Earth preserves our ancient structures. This preservation advantage means that evidence of ancient Martian civilizations, if it exists, might still be waiting to be discovered on the planet's surface. Unlike on Earth, where we must dig deep to find traces of ancient cultures, Martian ruins might still be visible on the surface, waiting for the right instruments and the right perspective to reveal their true nature. The possibility becomes even more compelling when we consider what geologists call deep time. The time frames we're discussing when we talk about ancient Mars aren't measured in thousands or even millions of years, but in billions of years. That's enough time for civilizations to rise, flourish, decline, and vanish multiple times over. On Earth, our entire recorded history spans only a few thousand years. Our species has existed for perhaps 300,000 years. Complex civilizations have existed for less than 10,000 years. But Mars was potentially habitable for periods measured in billions of years. That's 1,000 times longer than human civilization has existed. In such vast spans of time, multiple civilizations could have risen and fallen on Mars without leaving obvious traces. They could have developed, thrived, faced extinction events, and been replaced by new civilizations multiple times throughout Martian history. The Mars we see today might be the final chapter in a story that includes countless civilizations we know nothing about. This concept isn't purely speculative. Scientists have seriously considered whether advanced civilizations could vanish from the geological record over such timeframes. The idea has even acquired a name, the Silurian Hypothesis, named after an ancient species from the science fiction series Doctor Who. The Silurian Hypothesis asks a deceptively simple question. If an industrial civilization had existed on Earth millions of years ago, would we be able to detect evidence of it today? The surprising answer is that such evidence might be extremely difficult to find. Most of what we consider permanent features of human civilization would decay, erode, or be buried beyond recognition over geological timeframes. Our cities would crumble and be covered by sediments. Our roads would be ground down by erosion. Even our most durable materials would eventually succumb to chemical weathering and biological decay. After a few million years, almost all direct evidence of human civilization would disappear from Earth's surface. This realization has profound implications for our search for evidence of ancient Martian civilizations. If Earth's active geology could erase traces of industrial civilizations over geological time, then Mars's more stable surface conditions might actually preserve evidence better than Earth would. But that evidence might not look like what we expect to find. The monuments, buildings, and artifacts that we associate with ancient civilizations on Earth might not survive even on Mars over the time frames we're considering. Instead, scientists would need to look for more subtle traces, industrial byproducts that might persist in the geological record, isotopic anomalies that could indicate artificial nuclear processes, unusual concentrations of rare elements that might result from technological activities. These traces would be far more difficult to detect than obvious structures like the face on Mars, but they would also be far more conclusive if discovered. A building or monument could potentially be explained by natural processes, but certain types of industrial signatures would be unmistakable evidence of technological intelligence. The search for such evidence is just beginning, but it's being taken seriously by researchers who recognize that the question of ancient Martian civilizations isn't just idle speculation. It's a legitimate scientific inquiry that could revolutionize our understanding of life, intelligence, and the history of our solar system. As we continue our exploration of this fascinating possibility, we'll examine the evidence more closely, separate fact from fiction, and consider what kind of proof would be needed to confirm that Mars once hosted intelligent life. The implications of such a discovery would extend far beyond Mars itself, fundamentally changing how we think about the prevalence of intelligence in the universe and our own place in the cosmic story. The red planet keeps its secrets well, but modern science is developing the tools needed to unlock them. Whether those secrets include evidence of ancient civilizations remains to be seen, but the very fact that we can seriously ask the question represents one of the most exciting frontiers in contemporary science. But the search for ancient Martian civilizations faces a formidable opponent that has nothing to do with time, erosion, or geological processes. It's a quirk of human psychology that has led us astray countless times throughout history, yet continues to shape how we interpret mysterious images and unexplained phenomena. The enemy is pareidolia, our brain's remarkable ability to see familiar patterns where none actually exist. It's the same mental process that makes us see animals in cloud formations, faces in wood grain, and the man in the moon. Our pattern-seeking minds are so eager to find meaning and familiarity that they can transform random arrangements of light and shadow into seemingly purposeful designs. When researchers began taking higher resolution photographs of the famous face on Mars using more advanced cameras and different lighting conditions, the illusion began to crumble. NASA's Mars Global Surveyor captured detailed images in 1998 that revealed the face to be nothing more than an ordinary mesa, a flat-topped hill common throughout the American Southwest. The facial features that had seemed so obvious in the original Viking photograph were simply tricks of light and shadow, enhanced by the low resolution and specific angle of the sun when the original image was captured. Subsequent photographs from the Mars Reconnaissance Orbiter and the European Space Agency's Mars Express completely demolished any remaining mystery. The face on Mars, viewed from multiple angles and under different lighting conditions, bears no resemblance to an artificial structure. It's a perfectly natural geological formation that happened to create the illusion of a face under very specific photographic conditions. The deflation of the face on Mars might have ended speculation about Martian monuments, but it actually revealed something more profound about the challenge of searching for ancient civilizations on other worlds. If our own minds can so easily deceive us into seeing artificial structures where none exist, how can we develop reliable methods for identifying genuine evidence of extraterrestrial intelligence? This question becomes even more complex when we consider the vast differences between what ancient Martian civilizations might have built and what human civilizations typically construct. We naturally look for structures that resemble our own architectural traditions, pyramids, faces, geometric patterns that mirror human aesthetic preferences. But alien civilizations would have evolved under completely different environmental pressures and might have developed architectural styles that bear no resemblance to anything humans have ever built. Consider how human architecture reflects our specific biological needs and environmental challenges. We build doorways sized for human bodies, windows positioned at human eye level, stairs designed for human leg length and stride. We use materials and construction techniques adapted to Earth's gravity, atmospheric pressure, and weather patterns. Everything about human architecture reflects our evolutionary history and planetary environment. Martian civilizations would have faced entirely different constraints. If they evolved in Mars's lower gravity, they might have built structures that would seem impossible on Earth. If they developed during Mars' transition from a thick to thin atmosphere, their architecture might reflect adaptation to changing environmental conditions. Their aesthetic preferences, if they had any, might be based on sensory experiences completely alien to human perception. This realization forces us to expand our definition of what artificial structures might look like on Mars. Instead of searching for pyramids and faces, we need to develop new frameworks for recognizing intelligence that don't depend on human-centric assumptions about what civilizations should build or how they should modify their environment. Some researchers have proposed looking for mathematical relationships in Martian surface features that would be extremely unlikely to occur naturally. Geometric progressions in the spacing of rock formations, angles that consistently appear in multiples of specific numbers, symmetries that extend across distances too large to be explained by natural processes. Others suggest focusing on isotopic signatures that could indicate industrial activity. Nuclear processes, whether for energy production or weapons, leave distinctive traces in the atomic composition of materials that persist for millions of years. Advanced civilizations might have used nuclear technology extensively, creating isotopic anomalies that would still be detectable today. The concept extends beyond nuclear signatures to include any industrial byproducts that would be difficult to explain through natural processes. Unusual concentrations of rare earth elements, artificial compounds that don't occur naturally, trace amounts of manufactured materials that could only be produced through technological processes. But perhaps the most intriguing possibility involves what scientists call technosignatures, evidence of technology that operates on planetary scales. Advanced civilizations might have undertaken massive engineering projects that would leave permanent geology marks on their planet. Artificial channels carved through continents, systematic mining operations that altered the composition of entire mountain ranges, even terraforming efforts that changed atmospheric composition or surface chemistry. These planetary-scale modifications would be visible in Mars's geological record, but they would require sophisticated analysis to distinguish from natural processes. After all, many natural phenomena can create features that initially appear artificial. Volcanic activity can carve straight lines through landscapes. Crystalline structures can create geometric patterns. Even biological processes can sometimes produce formations that seem engineered. The challenge becomes separating genuine technosignatures from natural phenomena that merely appear artificial. This requires developing new analytical tools and statistical methods that can quantify the probability that observed features resulted from intelligent design rather than natural processes. Recent advances in artificial intelligence and machine learning offer promising approaches to this challenge. Computer algorithms can be trained to recognize patterns that human observers might miss, while avoiding the pareidolia effects that lead humans to see faces and structures where none exist. These systems can analyze vast amounts of data from orbital photographs, spectroscopic measurements, and geological surveys to identify anomalies that warrant further investigation. The European Space Agency's Mars Express mission has already demonstrated the potential of this approach by using automated pattern recognition to identify previously unknown geological features. Similar techniques could be adapted to search for signatures of ancient technological activity, processing the enormous datasets being collected by current and future Mars missions. But even if we develop perfect methods for detecting ancient technosignatures, we face another profound challenge: the sheer scale of deep time and what it does to evidence of intelligence. The Silurian Hypothesis, which we touched on earlier, suggests that even obvious signs of technological civilization can vanish completely over geological timeframes. The implications are staggering when applied to Mars. If Martian civilizations existed billions of years ago, during Mars's early habitable period, virtually all direct evidence of their existence might have been erased by subsequent geological processes. Even though Mars is more geologically stable than Earth, billions of years of dust storms, temperature cycles, and occasional impacts would gradually erase surface structures and artifacts. This doesn't mean evidence of ancient Martian civilizations would disappear entirely, but it would become increasingly subtle and difficult to detect. Industrial pollutants might survive in ice deposits or sedimentary layers. Artificial isotopes could persist in certain types of rock formations. Large-scale engineering projects might leave traces in subsurface geology even after surface evidence has vanished. The search for such evidence requires thinking about civilization in ways that extend far beyond our typical archaeological approaches. Instead of looking for temples and tools, scientists must search for the chemical and physical signatures that technological activities leave in planetary systems. Recent discoveries on Earth provide encouraging examples of how such signatures can persist across vast time frames. Geologists have found evidence of the Great Oxidation Event, a dramatic change in Earth's atmospheric chemistry that occurred over 2 billion years ago when photosynthetic organisms first began producing oxygen in large quantities. The chemical signatures of this biological revolution are still clearly visible in Earth's geological record. If biological processes can leave such persistent traces, technological processes should be equally detectable if we know what to look for. The key is developing sufficiently sophisticated analytical techniques and expanding our search to include the kinds of subtle signatures that advanced civilizations might have left behind. This brings us to a crucial question. What level of technological sophistication would be required to leave detectable traces over geological time? Would early agricultural civilizations leave any evidence, or would only industrial societies create signatures persistent enough to survive billions of years? The answer likely depends on the specific technologies employed and the scale at which they operated. Small-scale metal working or simple manufacturing might leave no detectable traces after millions of years. But large-scale mining, nuclear technology, or planetary engineering projects could create signatures that persist indefinitely. This suggests that our search for ancient Martian civilizations might be biased toward detecting only the most advanced and technologically sophisticated societies. Earlier civilizations that never developed industrial technology might be completely invisible to our current detection methods, regardless of how complex their social structures or how sophisticated their non-industrial technologies might have been. The bias has profound implications for how we interpret negative results in our search for Martian techno-signatures. The absence of detectable technological signatures wouldn't necessarily mean that Mars never hosted intelligent life. It might simply mean that Martian civilizations never developed the specific types of technology that leave geological signatures, or that they existed during periods when Mars' environmental conditions were less favorable for preserving such evidence. Despite these challenges, the scientific community is taking the search for ancient Martian civilizations increasingly seriously. NASA has begun incorporating techno-signature detection into its Mars exploration strategy, recognizing that evidence of past intelligence could be just as scientifically valuable as evidence of past microbial life. The implications of such a discovery would extend far beyond Mars itself. Finding evidence that intelligence had evolved independently on 2 planets in the same solar system would revolutionize our understanding of how common intelligence might be throughout the universe. It would suggest that the evolution of technological civilizations is not an extraordinarily rare accident, but a natural outcome when planets remain habitable for sufficient periods. Such a discovery would also raise profound questions about the relationship between intelligence and planetary survival. If Mars once hosted advanced civilizations, what happened to them? Did they succumb to the same environmental changes that made Mars uninhabitable? Did they escape to other worlds? Or did they somehow contribute to their own planet's environmental collapse? These questions connect directly to contemporary concerns about humanity's impact on Earth's climate and environment. If we could understand what happened to hypothetical Martian civilizations, we might gain crucial insights into the long-term sustainability of technological societies and the factors that determine whether intelligence can survive and thrive over cosmic timescales. The search for ancient Martian civilizations thus represents more than just curiosity about our neighboring planet. It's an investigation into the fundamental nature of intelligence in the universe and the ultimate fate of technological societies. The answers we find or don't find could profoundly influence how we think about our own civilization's future and our responsibilities as potentially the only known intelligence in our region of the galaxy. As our robotic emissaries continue their patient exploration of the red planet, each new discovery brings us closer to answering these profound questions. Whether Mars holds evidence of ancient intelligence remains unknown, but the very fact that we can seriously investigate this possibility represents one of the most exciting frontiers in contemporary science, where archaeology meets astrobiology in humanity's greatest detective story. But as we delve deeper into this cosmic mystery, we encounter evidence that forces us to confront possibilities that stretch the boundaries of everything we thought we knew about life in our solar system. Recent discoveries have revealed that Mars wasn't just wet in its distant past, it was actively, dynamically alive with geological processes that could have sustained complex ecosystems for unimaginable spans of time. In 2024, scientists using seismic data from NASA's InSight lander made a discovery that sent shockwaves through the scientific community. Deep beneath Mars's frozen surface, locked away in the planet's middle crust between 7 and 13 miles down, lies a vast reservoir of liquid water. Not ancient ice or trace moisture, but actual liquid water existing right now, today, in quantities so enormous they could cover the entire planet to a depth of over a mile. This isn't just another interesting geological finding. It's a revelation that fundamentally changes how we think about Mars' capacity to harbour life across vast stretches of time. If liquid water exists in Mars's subsurface today, under current hostile conditions, what might have been possible when the planet's surface was warm and wet? The implications become even more staggering when we consider recent analysis of Martian meteorites that have fallen to Earth. Scientists studying a famous specimen known as Black Beauty discovered something extraordinary: geochemical fingerprints of hot water activity dating back 4.45 billion years. This pushes evidence for habitable conditions on Mars back to the very dawn of the solar system, suggesting that Mars may have been suitable for life before Earth had even stabilized into a habitable world. These hot water systems aren't just evidence of ancient habitability. They represent exactly the kind of environment where life is most likely to emerge. On Earth, hydrothermal vents and hot springs are considered among the most probable locations for the origin of life. They provide concentrated minerals, diverse energy sources, and protective environments shielded from harsh surface conditions. If Mars hosted similar systems for billions of years, the probability that life emerged there becomes not just possible, but almost inevitable. But we're not talking about simple microbial life struggling to survive in extreme conditions. We're discussing ecosystems that could have thrived for geological ages, with timescales that dwarf the entire history of complex life on Earth. Consider the mathematics of deep time and biological evolution. Life on Earth went from simple cells to complex organisms in roughly 2 billion years. Human intelligence emerged from primitive mammals in just a few tens of millions of years. If Mars remained habitable for even half of its early history, that represents time spans of 2 billion years or more. Enough time for life to emerge, evolve into complex forms, develop intelligence, and potentially achieve technological sophistication that we can barely imagine. The evolutionary pressures that produced human intelligence in Earth's relatively brief habitable history would have had orders of magnitude more time to operate on Mars. The evidence for this extended habitability keeps mounting with each new discovery. NASA's Curiosity rover has found that ancient Mars experienced dramatic climate cycles rather than a gradual transition to its current frozen state. Water came and went in phases, creating environments that alternated between wet and dry conditions over millions of years. These cycles would have created evolutionary pressures that could have driven rapid adaptation and innovation among Martian life forms. Even more intriguingly, Curiosity has discovered organic molecules in sedimentary rocks dating back 3 billion years. These aren't just simple compounds, but complex carbon-based molecules that represent some of the fundamental building blocks of life. The discovery of boron on Mars adds another crucial piece to this puzzle, as boron is essential for the formation of RNA, one of the key molecules that enables life to store and transmit genetic information. Perhaps most compelling of all is the ongoing mystery of Martian methane. For years, different instruments have detected methane in Mars' atmosphere, sometimes in significant concentrations that spike dramatically and then disappear. On Earth, methane is primarily produced by biological processes. While geological processes can also create methane, the seasonal variations and temporary spikes observed on Mars suggest an active, ongoing source rather than passive release from ancient reservoirs. The methane detections remain controversial, with different missions reporting conflicting results. But if confirmed, they would indicate that something is actively producing methane on Mars today. Whether that something is geological or biological remains unknown, but the possibility that we're detecting the chemical signatures of contemporary Martian life cannot be dismissed. These discoveries paint a picture of Mars that is radically different from the dead, sterile world that most people imagine. Instead of a planet where life might have briefly emerged and quickly died out, we're looking at a world that could have hosted thriving ecosystems for billions of years, with some forms of life potentially persisting even today in subsurface environments. The implications for ancient Martian civilizations become profound when viewed against this backdrop of extended habitability. If Mars could support complex life for such vast periods, the evolution of intelligence becomes not just possible, but probable. And if intelligence did emerge on ancient Mars, it would have had timescales measured in geological epochs to develop and spread across the planet. This brings us to a crucial realization about the nature of evidence for ancient civilizations. The absence of obvious ruins or artifacts doesn't necessarily indicate the absence of past intelligence. Over the time scales we're discussing, even the most impressive monuments would likely be reduced to dust by natural processes. The Great Pyramid of Giza, one of humanity's most enduring achievements, has already suffered significant erosion in just a few thousand years. Over millions or billions of years, even the most massive structures would be worn away beyond recognition. But certain types of evidence could persist indefinitely. Industrial activities leave chemical signatures that can survive in geological formations for billions of years. Nuclear processes, whether natural or artificial, create distinctive isotopic ratios that serve as permanent fingerprints in rock and mineral deposits. Large-scale mining or manufacturing operations would alter the distribution of elements across planetary surfaces in ways that would remain detectable long after the civilizations responsible had vanished. Advanced civilizations might also have undertaken planetary engineering projects that would leave permanent marks on their world's geology. Artificial channels carved through continents, systematic alteration of atmospheric composition, or large-scale mining operations could create signatures that would persist even after all surface structures had eroded away. The search for such signatures represents a new frontier in archaeology, one that extends far beyond the traditional methods of digging up pottery shards and ancient buildings. Instead of looking for temples and tools, scientists must search for the chemical and physical traces that technological activities leave in planetary systems. Recent advances in analytical chemistry and spectroscopy are making such searches increasingly feasible. Instruments aboard current Mars missions can detect trace amounts of rare elements and identify isotopic anomalies that might indicate past industrial activity. Future missions will carry even more sophisticated analytical capabilities, potentially including instruments specifically designed to search for technosignatures. The European Space Agency's upcoming ExoMars rover will carry a drill capable of reaching 2 meters below the surface, accessing soil layers that have been protected from surface contamination for millions of years. If ancient Martian civilizations left industrial byproducts in the geological record, such protected samples might preserve evidence that surface analysis would miss. NASA's Perseverance rover is already collecting samples that will eventually be returned to Earth for detailed analysis in laboratories equipped with instruments far more sensitive than anything that can be sent to Mars. These samples could contain microscopic evidence of past technological activity that would be impossible to detect with current on-planet instruments. But perhaps the most intriguing evidence might come from places we haven't yet learned to look. Advanced civilizations might have developed technologies that operate according to principles we don't yet understand. They might have left behind traces that our current scientific frameworks can't recognize or interpret. Consider how a medieval scholar would struggle to identify evidence of modern industrial civilization. Plastic residues, radioactive isotopes from nuclear testing, and trace chemicals from modern manufacturing would be completely meaningless to someone without knowledge of contemporary technology. Similarly, evidence of advanced Martian technology might be present in our current data but remain invisible because we lack the conceptual frameworks needed to recognize it. This possibility suggests that the search for ancient Martian civilizations might require not just better instruments and more sophisticated analysis, but entirely new ways of thinking about what technological civilizations might accomplish and what traces they might leave behind. The stakes of this investigation extend far beyond Mars itself. If we could confirm that intelligence had evolved independently on 2 planets in the same solar system, it would revolutionize our understanding of life in the universe. Currently, we have only one example of intelligence, Earth, making it impossible to determine whether consciousness is a rare accident or a natural outcome of evolutionary processes. Finding evidence of ancient Martian intelligence would suggest that consciousness might be a common feature of planetary evolution, emerging whenever conditions remain suitable for sufficient periods. This would have profound implications for the search for extraterrestrial intelligence throughout the galaxy and could fundamentally alter how we think about humanity's place in the cosmic order. The discovery would also raise urgent questions about the relationship between intelligence and planetary survival. If Mars once hosted advanced civilizations, what happened to them? Did environmental changes beyond their control make their planet uninhabitable? Did they escape to other worlds? Or did they somehow contribute to their own planet's environmental collapse? These questions connect directly to contemporary concerns about climate change and environmental sustainability on Earth. Understanding what happened to hypothetical Martian civilizations could provide crucial insights into the long-term viability of technological societies and the factors that determine whether intelligence can survive and thrive over cosmic timescales. Some researchers have proposed that advanced civilizations might face what they call the Great Filter, a critical challenge that most intelligent species fail to overcome. If Mars once hosted civilizations that succumbed to such a filter, studying their fate could help us understand what challenges await our own species and how we might navigate them successfully. The possibility becomes even more compelling when we consider that Mars and Earth have exchanged material throughout their histories. Asteroid impacts have launched rocks from Mars that eventually fell to Earth as meteorites. If life existed on Mars, it's possible that Martian microorganisms could have traveled to Earth aboard these natural spacecraft, seeding our planet with life that originally evolved on Mars. This concept, known as panspermia, suggests that Earth and Mars might share a common biological heritage. If true, then studying Martian life, whether ancient or contemporary, could provide insights into the deepest origins of life on Earth. We might discover that we ourselves are descended from ancient Martian organisms, making Mars not just our planetary neighbour, but our ancestral home. Recent discoveries have made panspermia seem increasingly plausible. Scientists have found that some Earth organisms can survive the radiation and temperature extremes of space travel, and that the interiors of sufficiently large meteorites remain protected from the harsh conditions of interplanetary space. If life could travel from Mars to Earth, it could also travel from Earth to Mars, creating the possibility of ongoing biological exchange between our worlds. This interconnectedness means that the search for life on Mars isn't separate from understanding life on Earth. The two investigations are intimately connected, with discoveries on one world informing our understanding of the other. Finding evidence of ancient Martian civilizations wouldn't just tell us about Mars, it would fundamentally change how we understand the history and potential future of intelligence throughout our solar system. The implications extend even further when we consider the possibility that advanced Martian civilizations might have developed space travel capabilities. If they achieved technological sophistication during Mars' habitable period, they would have had millions or billions of years to develop interplanetary travel. They might have established colonies throughout the solar system, leaving traces of their presence on multiple worlds. This possibility transforms the search for ancient Martian intelligence from a single planet investigation into a solar system-wide archaeological project. Evidence of Martian civilizations might exist not just on Mars itself, but on the Moon, on asteroids, or even in the outer solar system, where conditions might have better preserved artifacts from ancient times. Some researchers have seriously proposed searching for such evidence in our own cosmic neighbourhood. The far side of the Moon, protected from Earth's geological activity and atmospheric weathering, could preserve structures or artifacts for billions of years. Ancient space stations or mining operations in the asteroid belt might still be detectable if we knew what to look for and where to search. These possibilities highlight how the question of ancient Martian civilizations connects to broader questions about the prevalence and longevity of intelligence in the universe. We're not just asking whether Mars once hosted life, but whether intelligence naturally emerges from biological evolution and whether technological civilizations can survive and spread across cosmic distances. The answers to these questions will shape humanity's future in ways we're only beginning to understand. If we discover that we're alone in our cosmic neighbourhood, it would place an enormous responsibility on our species to preserve and spread consciousness throughout the galaxy. If we find that intelligence has emerged multiple times in our solar system alone, it would suggest that the universe might be teeming with conscious beings, fundamentally changing our perspective on cosmic evolution and our role within it. As we continue pushing the boundaries of Mars exploration, each new mission brings us closer to answering these profound questions. Whether through chemical analysis of ancient rocks, deep drilling into subsurface reservoirs, or detailed mapping of surface formations, we're gradually assembling the pieces of Mars' ancient history. The red planet guards its secrets carefully, but human ingenuity and technological capability continue to advance at an exponential pace. Within the next few decades, we'll have capabilities for Mars exploration that would have seemed like science fiction just a generation ago. Advanced rovers, sample return missions, and eventually human exploration will provide unprecedented access to Martian geology and chemistry. But perhaps the most important developments will be conceptual rather than technological. As we learn more about the deep history of our solar system and the conditions that enable life to emerge and evolve, we're developing new frameworks for understanding what evidence of ancient intelligence might look like and where we should search for it. The investigation of ancient Martian civilizations represents more than just curiosity about our neighboring planet. It's an exploration of the fundamental nature of consciousness in the universe, and a search for our own cosmic origins and destiny. The answers we find will echo through human culture for generations to come, shaping how we think about life, intelligence, and our place in the vast cosmos that surrounds us. Every photograph from Mars, every chemical analysis, every geological survey contributes to this grand detective story. We're not just exploring another world, we're investigating whether consciousness has emerged elsewhere in our cosmic neighborhood, and what that might mean for the future of intelligence throughout the universe. The implications are staggering, and the investigation has only just begun. Tonight, we're confronting one of the most unsettling realizations in all of astrobiology. What if we've been asking the wrong questions about Mars? What if instead of wondering whether simple microbes once existed in ancient Martian pools, we should be investigating something far more profound and disturbing? Picture this scenario and it sink in. And I want you to really let advanced civilization thrives on Mars for millions of years. They build cities, develop technology, perhaps even achieve space travel. They have art, culture, science, philosophy. They contemplate the cosmos just as we do. And then something happens. Environmental collapse, resource depletion, cosmic catastrophe, or something we haven't even imagined. The civilization vanishes, their cities crumble, their technology corrodes away, and after enough time passes, every trace of their existence is erased from the planetary surface. How long would it take for all evidence of a technological civilization to disappear completely? The answer might shock you. Even on Earth, with our active geology and erosive processes, most traces of modern human civilization would vanish within a few million years. Our cities would crumble into dust. Our roads would be ground away by natural processes. Our satellites would decay from orbit. Even our most durable monuments would eventually succumb to the relentless forces of erosion and chemical weathering. This is the terrifying beauty of deep time. It doesn't just heal wounds in the geological record, it erases entire histories. Civilizations that once thought themselves permanent fixtures in the cosmos can vanish so completely that later species might never know they existed at all. This concept has acquired a name that should send chills down your spine: the Silurian Hypothesis. Named after an ancient species from science fiction, it poses a question that keeps astrobiologists awake at night. If an industrial civilization had existed on Earth millions of years ago, would we be able to detect any evidence of it today? The disturbing answer is probably not. Most direct evidence would be gone. Buildings reduced to unrecognizable sediments. Technology corroded beyond identification. Even nuclear waste, which we consider among our most persistent pollutants, would decay to undetectable levels over geological timeframes. But here's where the investigation takes a fascinating turn. While obvious artifacts might disappear, certain types of evidence could persist indefinitely. Industrial byproducts leave chemical signatures in sedimentary layers. Nuclear processes create distinctive isotopic ratios that serve as permanent fingerprints. Large-scale mining operations alter the distribution of elements in ways that remain detectable long after the miners themselves have vanished. On Mars, these subtle signatures might be even better preserved than on Earth. Mars lacks the active plate tectonics that constantly recycle Earth's crustal material. It doesn't have flowing water to wash away chemical traces. Its thin atmosphere provides less weathering action to erode geological formations. In many ways, Mars is a better museum for preserving ancient evidence than Earth could ever be. This preservation advantage creates a tantalizing possibility. If ancient Martian civilizations existed, traces of their industrial activities might still be detectable in the planet's geological record. Not obvious ruins or recognizable artifacts, but chemical and isotopic signatures that could only result from technological processes. What would these signatures look like? Scientists have identified several categories of evidence that would be virtually impossible to explain through natural processes alone. Unusual concentrations of rare earth elements that don't match known geological patterns. Artificial isotopes created through nuclear reactions that don't occur naturally. Specific ratios of industrial metals that would indicate large-scale manufacturing or processing activities. Perhaps most compelling would be evidence of planetary-scale engineering projects. Advanced civilizations might have undertaken massive alterations to their planet's surface or atmosphere. These modifications would leave permanent marks in the geological record that would persist long after the civilizations responsible had vanished. Consider the kinds of projects that sufficiently advanced societies might attempt. Artificial channels carved across continents to redirect water flow. Systematic mining operations that altered the composition of entire mountain ranges. Atmospheric engineering projects that changed the chemical composition of the planet's air. Even terraforming efforts designed to make their world more hospitable to life. Such projects would require technologies and energy expenditures that dwarf anything human civilization has yet achieved. But given millions of years to develop, what might be possible? On Earth, we've already begun modifying our planet's atmosphere through industrial activities, and we've only had advanced technology for a couple of centuries. What might civilizations accomplish with millions of years of technological development? The search for these subtle techno-signatures represents a completely new approach to archaeology. Instead of digging up pottery and tools, scientists must analyze chemical compositions and isotopic ratios. Instead of looking for temples and monuments, they search for industrial pollutants and nuclear byproducts, making such searches increasingly feasible. Mass. Recent advances in analytical chemistry are spectrometry can detect trace amounts of elements at concentrations measured in parts per billion. Isotopic analysis can identify artificial nuclear processes even when they occurred billions of years ago. Advanced computer algorithms can process vast datasets to identify statistical anomalies that might indicate technological activity. But the most intriguing evidence might not be chemical at all, it might be mathematical. Advanced civilizations would likely leave behind patterns and relationships that would be extremely unlikely to occur through natural processes alone. Geometric progressions in the spacing of surface features. Angular relationships that consistently appear in multiples of specific numbers. Symmetries that extend across distances too vast to be explained by geological coincidence. These mathematical signatures would be far more subtle than the obvious geometric patterns that early researchers thought they saw in Martian surface features. They would require sophisticated statistical analysis to detect and would need to be confirmed through multiple independent observations. But if genuine, they would provide compelling evidence for technological intelligence operating on planetary scales. The implications of discovering such evidence would extend far beyond Mars itself. Finding proof that intelligence had evolved independently on two planets in the same solar system would revolutionize our understanding of consciousness in the universe. Currently, we have only one example of technological civilization, making it impossible to determine whether intelligence is a rare accident or a natural outcome of evolutionary processes. But discovering ancient Martian techno-signatures would also raise deeply unsettling questions about the ultimate fate of technological civilizations. If Mars once hosted advanced societies, what happened to them? Did they succumb to environmental collapse as their planet's climate changed? Did they face resource depletion that their technology couldn't overcome? Or did they encounter some other barrier that we haven't yet imagined? These questions connect directly to humanity's current predicament on Earth. We're facing our own environmental challenges, resource limitations, and technological risks. Understanding what happened to hypothetical Martian civilizations could provide crucial insights into whether technological intelligence can survive and thrive over cosmic timescales, or whether it inevitably leads to self-destruction. Some researchers have proposed that advanced civilizations face what they call existential filters, critical challenges that most intelligent species fail to navigate successfully. Climate change, nuclear warfare, artificial intelligence, biotechnology disasters, resource depletion. Each represents a potential trap that could end technological civilization permanently. If Mars once hosted civilizations that succumbed to such filters, studying their fate becomes more than just archaeological curiosity. It becomes essential research for our own survival. We need to understand what challenges await technological species and how those challenges might be overcome. The search for ancient Martian techno-signatures thus represents one of the most important investigations in contemporary science. We're not just exploring the history of another planet. We're investigating the fundamental nature of intelligence in the universe and the factors that determine whether conscious beings can achieve long-term survival and prosperity. Recent missions to Mars have begun incorporating this perspective into their scientific objectives. NASA's Perseverance rover is collecting samples that will eventually be returned to Earth for analysis in laboratories equipped with the most sensitive analytical instruments ever created. These samples could contain microscopic evidence of past technological activity that would be impossible to detect with current on-planet capabilities. The European Space Agency's upcoming missions will carry instruments specifically designed to search for chemical and isotopic anomalies that might indicate past industrial processes. Future Mars exploration will increasingly focus not just on signs of ancient life, but on evidence of ancient intelligence. But perhaps the most important developments will be conceptual rather than technological. As we learn more about how civilizations might alter their planetary environments and what traces such alterations might leave behind, we're developing new frameworks for recognizing technological signatures in geological records. The investigation requires expanding our definition of what constitutes archaeological evidence. Traditional archaeology focuses on objects created by intelligent beings, tools, pottery, buildings, art. But planetary archaeology must look for the environmental consequences of intelligent activity. Chemical pollution, isotopic anomalies, large-scale landscape modifications, atmospheric alterations. This expanded definition opens up entirely new categories of evidence that previous generations of researchers never considered. Industrial activities inevitably alter the chemical composition of their surrounding environment. Nuclear processes leave permanent isotopic fingerprints. Large-scale construction projects modify surface geology in detectable ways. Advanced civilizations might also have developed technologies that operate according to principles we don't yet understand. They might have left behind evidence that our current scientific frameworks can't recognize or interpret. Consider how a medieval scholar would struggle to identify traces of modern industrial civilization. Plastic residues, artificial radioisotopes, trace chemicals from manufacturing processes would be completely meaningless without knowledge of contemporary technology. Similarly, evidence of advanced Martian technology might be present in our current data, but remain invisible because we lack the conceptual tools needed to recognize it. This possibility suggests that the search for ancient techno-signatures might require not just better instruments, but entirely new ways of thinking about what technological civilizations might accomplish. The stakes of this investigation become even higher when we consider the possibility that Mars and Earth might have exchanged not just rocks, but living organisms throughout their histories. Asteroid impacts have launched material from Mars that eventually reached Earth as meteorites. If life existed on Mars, Martian microorganisms could have traveled to Earth aboard these natural spacecraft. This process, known as panspermia, suggests that life on Earth and Mars might share common ancestry. If true, then discovering evidence of ancient Martian civilizations wouldn't just tell us about another world. It would provide insights into our own deepest origins and evolutionary history. The possibility becomes even more intriguing when we consider that panspermia might have involved not just primitive microorganisms, but genetic material from advanced life forms. If Martian civilizations achieved sophisticated biotechnology before their extinction, they might have deliberately seeded other worlds with genetic information designed to eventually produce intelligence. Such directed panspermia would represent the ultimate form of civilizational survival. Even if the parent civilization couldn't escape their dying world, they might ensure that their genetic and cultural legacy continued on other planets. Earth life, including human intelligence, might represent the flowering of ancient Martian civilization in a new planetary environment. These speculations highlight how the search for ancient Martian technosignatures connects to the deepest questions about human origins and destiny. We're not just investigating whether other worlds once hosted intelligence, we're exploring the possibility that we ourselves might be the descendants of ancient cosmic travelers. The implications would transform how we think about our responsibilities as potentially the only known intelligence in our cosmic neighborhood. If we carry within ourselves the genetic legacy of ancient Martian civilizations, then preserving and spreading consciousness throughout the galaxy becomes not just an opportunity, but an obligation to our cosmic ancestors. Recent discoveries have made these possibilities seem increasingly plausible, rather than purely speculative. The detection of subsurface liquid water on contemporary Mars suggests that the planet might still harbor life in protected underground environments. Complex organic molecules found in ancient Martian rocks indicate that the chemical building blocks for life were abundant on ancient Mars. Most intriguingly, the ongoing detection of methane in Mars' atmosphere suggests that something is actively producing this gas today. While geological processes can create methane, biological processes are far more efficient producers. The seasonal variations and temporary spikes observed in Martian methane suggest active sources rather than passive release from ancient reservoirs. If confirmed, these methane detections might indicate that Mars still hosts living organisms in subsurface environments, but they could also represent something even more extraordinary. What if the methane is being produced not by simple microorganisms, but by descendants of ancient Martian life forms that survived their civilization's collapse by retreating underground? This possibility transforms our understanding of what we might discover on Mars. Instead of just searching for fossil evidence of ancient life, we might be on the verge of encountering the living descendants of civilizations that thrived billions of years ago. These organisms might carry within their genetic codes information about their technological ancestors, providing direct links to vanished worlds of intelligence and culture. The search for ancient Martian civilizations thus represents far more than archaeological curiosity. It's an investigation into the fundamental nature of consciousness in the universe and humanity's place within cosmic evolution. Whether we find evidence of vanished technological societies or discover that we're truly alone in our cosmic neighborhood, the answers will profoundly shape how we think about intelligence, survival, and our responsibilities as conscious beings. Every sample collected, every chemical analysis performed, every statistical pattern detected contributes to this grand investigation. We're not just exploring another planet, we're searching for evidence that consciousness has emerged elsewhere in our cosmic vicinity and trying to understand what that means for the future of intelligence throughout the universe. The Red Planet continues to guard its secrets, but human ingenuity and determination continue advancing toward answers that will echo through our culture for generations to come. Whether Mars once hosted civilizations that achieved wonders we can barely imagine, or whether it remained forever lifeless despite its early promise. The investigation itself represents humanity at its best, curious, persistent, and unwilling to accept easy answers to the universe's deepest mysteries. As we push deeper into this cosmic detective story, each new discovery brings us closer to understanding not just what happened on ancient Mars, but what possibilities await intelligence throughout the galaxy. The implications are staggering, the investigation is accelerating, and the answers, when they come, will fundamentally change how we understand our place in the vast, mysterious, and potentially populated cosmos that surrounds us. But as we stand at the threshold of potentially revolutionary discoveries, we must confront a possibility that challenges everything we think we understand about the search for ancient intelligence. What if the evidence we're seeking isn't just hidden beneath Mars' surface, but actively being destroyed by our own methods of investigation? Consider the Viking missions of 1976, humanity's first direct attempt to search for life on Mars. These pioneering spacecraft carried sophisticated biological experiments designed to detect microbial activity in Martian soil. One of these experiments, the labeled release test, produced results that seemed to indicate biological processes at work. When nutrients were added to soil samples, radioactive carbon dioxide was released at levels thousands of times higher than background radiation, exactly what would be expected if living organisms were consuming the nutrients and releasing waste products. The results met every pre-mission criterion for a positive detection of life. Yet the scientific community ultimately concluded that the Viking missions had found no evidence of biology on Mars. Why? Because other experiments failed to detect organic compounds in the soil, leading researchers to assume that chemical rather than biological processes must have caused the positive results. For decades, this interpretation seemed settled. Mars was sterile, at least in the locations where Viking had landed. The positive biological signals were dismissed as artifacts of Martian chemistry that we didn't yet fully understand. Case closed, but then came a discovery that changed everything. In 2008, the Phoenix lander detected something in Martian soil that no one had anticipated: perchlorates, highly reactive chemical compounds that make up nearly 0.5% of the soil by weight. When heated, as they were in the Viking molecular analysis experiments, perchlorates destroy organic compounds almost instantly, breaking them down into simple molecules that would be virtually undetectable. This revelation sent shockwaves through the astrobiology community. The absence of organic compounds that led scientists to dismiss the Viking biological results might not indicate the absence of life at all. Instead, it might mean that any organic material present was being destroyed by the very process designed to detect it. Some researchers now argue that the Viking experiments might have actually killed Martian organisms by exposing them to conditions they couldn't survive. If Mars hosts life forms adapted to the planet's hyper-arid conditions, adding water and nutrients in a laboratory setting might be as lethal to them as extreme dehydration would be to terrestrial organisms. This reinterpretation of the Viking results highlights a fundamental challenge in searching for evidence of ancient Martian civilizations. Our investigative methods are necessarily based on our understanding of how life and technology operate on Earth. But what if Martian biology and technology developed along completely different pathways? The implications extend far beyond simple microbial detection. If we're inadvertently destroying evidence of current Martian life with our analytical techniques, what might we be missing when we search for traces of ancient civilizations? Industrial byproducts that seem stable might decompose under analysis conditions we consider routine. Technological materials might react with terrestrial laboratories in ways that obliterate rather than reveal their artificial origins. This possibility forces us to reconsider every aspect of how we search for ancient techno-signatures. Instead of assuming that evidence of past civilizations would be recognizable using Earth-based analytical frameworks, we need to develop investigation methods that can detect truly alien forms of technology and industry. Recent advances in non-invasive analysis techniques offer promising approaches to this challenge. Spectroscopic methods can identify chemical compositions without physically altering samples. X-ray crystallography can reveal molecular structures while leaving materials intact. Advanced imaging techniques can detect internal features without destroying the objects being studied. But perhaps most importantly, we're beginning to understand that the search for ancient Martian civilizations requires thinking about technology in ways that transcend our own technological experience. Human industry is based on specific materials, energy sources, and manufacturing processes that reflect our evolutionary history and planetary environment. Alien technology might operate according to completely different principles. Consider how different human technology might have been if we had evolved under different conditions. If Earth had weaker gravity, we might have developed materials and construction techniques optimized for low-weight applications. If our atmosphere had different composition, our metallurgy and chemistry would follow different pathways. If our planet had different energy sources available, our entire technological development would have taken alternative directions. Martian civilizations would have faced environmental conditions unlike anything in human experience. Lower gravity would make certain types of construction easier while making others more challenging. Different atmospheric composition would drive the development of alternative materials and manufacturing processes. Unique energy sources might lead to technologies that operate on principles we haven't discovered. This technological diversity means that evidence of ancient Martian industry might not resemble anything we recognize as artificial. Instead of looking for familiar materials like metals and ceramics, we might need to search for substances and structures that have no terrestrial analogies. The challenge becomes identifying which features of the Martian environment represent natural geological processes and which might indicate technological modification. This requires developing statistical methods that can quantify the probability that observed features resulted from intelligent design rather than natural formation. Machine learning algorithms show particular promise for this type of analysis. Computer systems can be trained to recognize patterns that human observers might miss while avoiding the pareidolia effects that lead people to see faces and structures where none exist. These systems can process enormous data sets, from orbital photography and spectroscopic surveys to identify anomalies that warrant further investigation. The European Space Agency's Mars Express mission has already demonstrated the potential of automated pattern recognition by discovering previously unknown geological features through computer analysis of photographic data. Similar techniques could be adapted to search for signatures of ancient technological activity. But even the most sophisticated analytical methods face limitations when dealing with evidence that might be billions of years old. The Silurian Hypothesis reminds us that even obvious signs of technological civilization can vanish completely over geological timeframes. On Mars, where conditions are more stable than Earth, evidence might persist longer, but it would still become increasingly subtle and difficult to detect over cosmic timescales. This temporal challenge means that our best hope for detecting ancient Martian civilizations might lie not in searching for direct artifacts, but in looking for the kinds of large-scale modifications that would leave permanent marks in the planet's geological record. Planetary engineering projects, systematic resource extraction, or atmospheric manipulation could create signatures that would persist even after all surface structures had eroded away. Recent research into Earth's geological record provides encouraging examples of how technological signatures can survive across vast time periods. Scientists have identified chemical markers of the Industrial Revolution in ice cores and sedimentary deposits. These anthropogenic signals are clearly distinguishable from natural background variations and demonstrate how technological activities leave detectable traces in planetary systems. If human industrial activity operating for only a few centuries, can create detectable geological signatures, then Martian civilizations, with millions of years of development time, would likely leave much more prominent traces. The challenge lies in developing the analytical techniques and conceptual frameworks needed to recognize these signatures when we encounter them. The search is further complicated by the possibility that advanced Martian civilizations might have deliberately concealed evidence of their existence. If they recognized that their planet was becoming uninhabitable, they might have made conscious efforts to minimize their environmental impact or to hide traces of their technology from future investigators. Alternatively, they might have developed technologies that operate on principles so different from human understanding that their artifacts wouldn't be recognizable as artificial products. Biological engineering might have enabled them to grow structures rather than build them. Nanotechnology could have created materials that appear identical to natural substances. Quantum manipulation might have allowed them to alter matter in ways that leave no detectable traces. These possibilities highlight the fundamental epistemological challenge facing anyone who searches for evidence of ancient alien civilizations. How do you look for something when you don't know what it might look like, where it might be found, or even whether it exists at all? The answer might lie in casting the widest possible net while maintaining rigorous scientific standards for evaluating potential evidence. Instead of searching for specific types of artifacts or structures, researchers are developing methods for detecting any deviation from expected natural patterns, regardless of what might have caused those deviations. This approach requires comprehensive baseline studies of natural Martian processes so that anomalies can be identified and investigated. It also demands sophisticated statistical methods that can distinguish between random variations and patterns that might indicate intelligent causation. Current Mars missions are beginning to incorporate these principles into their scientific objectives. The Perseverance rover is systematically documenting the geological and chemical characteristics of its exploration area, creating detailed records that future researchers can use to identify unusual features. The samples it's collecting will provide unprecedented opportunities for laboratory analysis using the most sensitive instruments available. Future missions will expand this systematic approach across larger areas of the Martian surface. Orbital surveys are becoming increasingly detailed, with resolution capabilities that can detect features smaller than a few meters across. Advanced spectrometers can identify chemical compositions from orbit, enabling comprehensive mapping of surface and atmospheric chemistry. But perhaps the most important development is the growing recognition that the search for ancient Martian civilizations represents a legitimate scientific endeavor worthy of serious investigation. While extraordinary claims require extraordinary evidence, the question of whether intelligence has emerged elsewhere in our solar system is too important to dismiss without thorough investigation. The implications extend far beyond academic curiosity about Mars' ancient history. Understanding whether technological civilizations can emerge, thrive, and survive over cosmic timescales has direct relevance to humanity's own future prospects. If we discover that Mars once hosted advanced societies that ultimately failed to prevent their planet's environmental collapse, it would provide crucial insights into the challenges facing technological species. Conversely, if we find evidence that Martian civilizations successfully adapted to their changing environment or escaped to other worlds, it would suggest that the obstacles facing technological species are not insurmountable. Such discoveries could inform strategies for ensuring humanity's long-term survival and expansion beyond Earth. The search also connects to broader questions about the prevalence of intelligence in the universe. If consciousness emerged independently on both Earth and Mars, it would suggest that intelligence might be a natural outcome of biological evolution under suitable conditions. This would have profound implications for the search for extraterrestrial intelligence throughout the galaxy. Recent discoveries of potentially habitable exoplanets, have revealed that worlds capable of supporting liquid water are far more common than previously thought. If intelligence readily emerges on such worlds, the universe might be teeming with technological civilizations. Understanding how such civilizations develop and what challenges they face becomes crucial for predicting humanity's place in this larger cosmic community. The investigation of ancient Martian civilizations thus represents more than just planetary archaeology. It's an exploration of the fundamental nature of consciousness in the universe and the ultimate fate of intelligence itself. Whether we find evidence of vanished technological societies or discover that consciousness has emerged only once in our cosmic neighborhood, the answers will profoundly influence how we think about our own species' future. As robotic explorers continue their patient investigation of the Red Planet, each new discovery contributes to this grand scientific endeavor. Chemical analyses reveal the planet's ancient environmental conditions. Geological surveys map the history of water and volcanic activity. Atmospheric studies track how Mars transformed from a potentially habitable world to its current frigid state. The data accumulating from these investigations is creating an increasingly detailed picture of Mars' billions-year history. Within this vast temporal canvas, windows of habitability emerge during which complex life and potentially intelligence could have flourished. The challenge now lies in determining whether these windows were ever actually occupied by conscious beings. The answer may come from unexpected directions. Recent detection of seasonal methane variations in Mars' atmosphere suggests that something is actively producing this gas today. While geological processes can create methane, the patterns observed are more consistent with biological sources. If contemporary Mars still hosts living organisms, they might represent descendants of ancient life forms that survived their planet's environmental transformation. These potential survivors could carry within their genetics and biochemistry information about Mars' biological history. If ancient Martian civilizations existed, traces of their existence might persist not just in geological formations, but in the genomes of organisms that have maintained continuous evolutionary lineages since the planet's habitable period. The possibility transforms the search for ancient Martian intelligence from purely archaeological investigation to active biological exploration. Instead of only looking for fossilized remains of past civilizations, researchers might be on the verge of discovering living libraries that preserve information about their technological ancestors. Such discoveries would revolutionize our understanding of how intelligence and civilization relate to planetary evolution. They would provide direct insights into how conscious beings adapt to changing environmental conditions and what strategies enable the long-term survival of technological species. The investigation continues with each passing day, bringing new data, new analytical techniques, and new theoretical frameworks for understanding what we might find. The Red Planet guards its secrets carefully, but human curiosity and ingenuity are gradually unlocking mysteries that have remained hidden for billions of years. Whether Mars once hosted civilizations that achieved wonders we can barely imagine, or whether it remained forever uninhabited despite its early promise, the search itself represents humanity at its most ambitious. We're not just exploring another world, but investigating the deepest questions about consciousness, survival, and our place in a universe that might be far more populated with intelligence than we have ever dared to imagine. The implications of this investigation will echo through human culture for generations to come, shaping how we understand our cosmic significance and our responsibilities as potentially the most advanced known intelligence in our region of the galaxy. In laboratories and mission control centers around the world, scientists continue pushing the boundaries of what's possible in our quest to answer one of the most profound questions ever asked. Are we alone, or have we simply been looking in the wrong places for evidence of our cosmic neighbors? Tonight, as Mars rises in the sky above you, remember that you're looking at a world that might hold the answers to humanity's deepest questions about intelligence, survival, and the ultimate fate of consciousness in an ancient and mysterious universe. But as we delve deeper into this cosmic mystery, we encounter something that should make every thinking person pause and consider the true magnitude of what we're investigating. The question isn't just whether Mars once hosted civilizations, but whether we would even be capable of recognizing the evidence if it were staring us in the face. Consider the profound challenge of deep time and what it does to evidence. When we think about ancient civilizations on Earth, we're typically discussing cultures that existed thousands of years ago. The pyramids of Egypt, the ruins of Rome, the stone circles of ancient Britain. These monuments seem incredibly ancient to us, and yet they represent merely the blink of an eye in geological terms. If we expand our perspective to truly cosmic timescales, the picture becomes both humbling and terrifying. Mars was potentially habitable not thousands or even millions of years ago, but billions of years ago. We're talking about time frames that dwarf the entire history of complex life on Earth. During such vast periods, entire civilizations could rise, flourish, achieve technological sophistication that dwarfs our own, and then vanish completely without leaving a trace that our current methods could detect. This brings us to one of the most unsettling concepts in modern astrobiology, something that researchers have dubbed the Silurian Hypothesis. Named after an ancient reptilian species from science fiction, this hypothesis poses a question that keeps scientists awake at night. If an advanced industrial civilization had existed on Earth just 10 million years ago, would we be able to find any evidence of it today? The answer is deeply disturbing. Most likely, we would find nothing at all. Think about what would remain of our current civilization if it were subjected to 10 million years of geological processes. Our cities would crumble and be buried under sediments. Our roads and bridges would erode away. Our monuments would be ground down by wind and weather. Even our most durable materials would eventually succumb to chemical weathering and decay. After 10 million years, virtually all direct evidence of human technology would have vanished from Earth's surface. Our plastic pollution would have broken down. Our nuclear waste would have decayed to background levels. Our satellites would have long since fallen from orbit and disintegrated. Future geologists might detect subtle chemical anomalies in sedimentary layers, but they would be hard-pressed to conclude that these traces indicated the former existence of a technological civilization. Now multiply that time frame by a factor of several hundred. That's the temporal gulf we're dealing with when we consider the possibility of ancient Martian civilizations. We're not just looking for evidence that has survived a few million years of geological processes. We're searching for traces that might have persisted for billions of years through cosmic bombardments, climate transitions, and the gradual transformation of an entire planet. The mathematical probability that obvious artifacts would survive such timeframes approaches zero. Any surface structures would have been obliterated long ago by dust storms, temperature cycles, and the occasional asteroid impact. Buried artifacts would have been crushed, corroded, or chemically altered beyond recognition. Even the most durable materials imaginable would have been reduced to unrecognizable components in the planetary substrate. Yet this apparent hopelessness contains within it a glimmer of possibility that makes the search worthwhile. While obvious artifacts might disappear over cosmic timescales, certain types of evidence could persist indefinitely. Industrial activities leave chemical signatures that can survive in geological formations for billions of years. Nuclear processes create distinctive, isotopic ratios that serve as permanent fingerprints in rock and mineral deposits. Large-scale modifications to planetary systems could create patterns that remain detectable long after their creators have vanished. This realization has led researchers to develop entirely new approaches to searching for evidence of ancient technological civilizations. Instead of looking for recognizable artifacts or structures, they're developing methods to detect the subtle chemical and physical traces that industrial activities leave in planetary environments. Consider what kinds of signatures an advanced civilization might leave behind. Large-scale mining operations would alter the distribution of metals and rare earth elements across planetary surfaces. Industrial manufacturing would create unusual concentrations of specific chemical compounds. Nuclear technology would produce artificial isotopes that don't occur in nature. Atmospheric engineering projects could leave permanent traces in ice deposits or sedimentary layers. Even more intriguingly, planetary-scale engineering projects could create modifications that would remain visible in geological surveys for billions of years. Artificial channels carved across continents, systematic alteration of surface chemistry, or large-scale atmospheric manipulation could leave signatures that would persist even after all surface structures had been erased by natural processes. The search for such signatures requires analytical techniques that push the boundaries of current scientific capability. Mass spectrometry can now detect trace elements at concentrations measured in parts per trillion. Isotopic analysis can identify artificial nuclear signatures even when they're overwhelmed by natural background radiation. Advanced computer algorithms can process vast datasets to identify statistical patterns that might indicate technological modification of planetary systems. Recent missions to Mars have begun incorporating these approaches into their scientific objectives. The Curiosity and Perseverance rovers carry instruments capable of detecting chemical anomalies that previous generations of spacecraft would have missed entirely. They're systematically analyzing soil and rock samples for isotopic ratios, trace element distributions, and organic compounds that might preserve evidence of ancient biological or technological activity. But perhaps the most promising avenue for detecting ancient Martian technosignatures lies in the vast quantities of subsurface water that recent discoveries have revealed. Remember that enormous underground reservoir detected by the InSight lander, containing enough liquid water to cover the entire planet to a depth of over a mile. Such protected environments could preserve chemical evidence that surface conditions would have destroyed long ago if ancient Martian civilizations utilized groundwater resources for industrial purposes. Traces of their activities might still be detectable in these subsurface reservoirs. Industrial pollutants, artificial chemical compounds, or unusual isotopic signatures could persist in groundwater systems for geological ages, protected from the surface processes that would otherwise erase such evidence. The implications of discovering such technosignatures would extend far beyond Mars itself. Finding proof that technological intelligence had evolved independently on two planets in the same solar system would revolutionize our understanding of consciousness in the universe. Currently, we have only one example of technological civilization, making it impossible to determine whether intelligence represents a rare cosmic accident or a natural outcome of evolutionary processes. But confirming the existence of ancient Martian civilizations would also raise profound and troubling questions about the ultimate fate of technological species. If Mars once hosted advanced societies, what happened to them? Did they succumb to the environmental changes that transformed their planet from a warm, wet world into the frozen desert we see today? Did they face resource depletion or technological catastrophes that their science couldn't overcome? These questions connect directly to contemporary concerns about humanity's long-term prospects on Earth. We're currently facing our own environmental challenges, resource limitations, and technological risks. Understanding what happened to hypothetical Martian civilizations could provide crucial insights into whether technological intelligence can survive and thrive over cosmic timescales, or whether it inevitably leads to self-destruction. Some researchers have proposed that advanced civilizations face what they call great filters, critical challenges that most intelligent species fail to navigate successfully: climate change, nuclear warfare, resource depletion, artificial intelligence risks, biotechnology disasters. Each represents a potential trap that could end technological civilization permanently. If ancient Martian societies succumbed to such filters, studying their fate becomes essential research for our own survival. We need to understand what specific challenges await technological species and how those challenges might be successfully overcome. The Red Planet might serve as a cautionary tale, showing us what happens when civilizations fail to solve the fundamental problems of long-term sustainability. Alternatively, if we could find evidence that Martian civilizations successfully adapted to their changing planetary environment, it would suggest that the obstacles facing technological species are not insurmountable. Such discoveries could inform strategies for ensuring humanity's long-term survival and expansion beyond Earth. But the investigation faces challenges that extend beyond the obvious difficulties of detecting billion-year-old techno-signatures. One of the most significant obstacles is conceptual rather than technical. We're searching for evidence of technologies that might operate according to principles we don't understand, created by minds that evolved under completely different environmental pressures. Human technology reflects our specific evolutionary history and planetary environment. We build structures sized for human bodies, adapted to Earth's gravity and atmospheric conditions. We use materials and energy sources that happen to be available on our particular world. Everything about our technological development has been shaped by the unique circumstances of our species and our planet. Martian civilizations would have faced entirely different constraints and opportunities. Lower gravity would have made certain types of construction easier, while creating different structural challenges. Alternative atmospheric chemistry would have driven the development of different materials and manufacturing processes. Unique energy sources might have led to technologies that operate on principles we haven't discovered. This technological diversity means that evidence of ancient Martian industry might not resemble anything we would recognize as artificial. Instead of familiar materials like metals and ceramics, we might need to search for substances and structures that have no terrestrial analogies. The very categories we use to distinguish between natural and artificial might be inadequate for recognizing truly alien technology. The challenge becomes even more complex when we consider that advanced civilizations might have deliberately minimized their environmental impact. If Martian societies recognized that their planet was becoming uninhabitable, they might have made conscious efforts to develop sustainable technologies that left minimal traces in the geological record. Alternatively, they might have achieved such sophisticated control over matter and energy that their technological artifacts would be indistinguishable from natural materials. Biological engineering could have enabled them to grow structures rather than build them. Nanotechnology might have created materials that appear identical to naturally occurring substances. Quantum manipulation could have allowed them to alter matter in ways that leave no detectable signatures. These possibilities highlight the fundamental epistemological challenge facing anyone who searches for evidence of ancient alien civilizations. How do you look for something when you don't know what it should look like, where it might be found, or even whether it exists at all? The answer lies in developing increasingly sophisticated methods for detecting any deviation from expected natural patterns, regardless of what might have caused those deviations. Instead of searching for specific types of artifacts, researchers are learning to identify statistical anomalies that might indicate intelligent modification of planetary systems. This approach requires comprehensive understanding of natural Martian processes so that genuine anomalies can be distinguished from normal geological variation. It also demands advanced mathematical techniques that can quantify the probability that observed features resulted from intelligent design rather than natural formation. Machine learning algorithms show particular promise for this type of analysis. Computer systems can be trained to recognize subtle patterns that human observers might miss while avoiding the pareidolia effects that lead people to see faces and structures in random formations. These systems can process enormous datasets from orbital photography, spectroscopic surveys, and geological measurements to identify features that warrant further investigation. Current Mars missions are generating unprecedented amounts of data that will keep researchers busy for decades. High-resolution photographs reveal surface details smaller than a few meters across. Spectroscopic analysis can identify chemical compositions from orbit with remarkable precision. Subsurface radar can map geological structures hidden beneath layers of dust and rock. As this information accumulates, patterns are beginning to emerge that paint an increasingly detailed picture of Mars' ancient history. We're learning that the planet's transition from habitable to hostile wasn't a gradual decline, but a series of dramatic climate shifts punctuated by periods of relative stability. During these stable intervals, conditions might have remained suitable for complex life and potentially intelligence for millions or tens of millions of years at a time. These windows of habitability create intriguing possibilities for the development and survival of advanced civilizations. Even if individual societies couldn't prevent their planet's ultimate environmental collapse, they might have persisted long enough to achieve remarkable technological sophistication. They could have developed space travel capabilities, established colonies on other worlds, or found ways to survive in protected subsurface environments. The possibility that descendants of ancient Martian civilizations might still exist somewhere in our solar system adds another dimension to the search. Instead of only looking for fossilized evidence of extinct societies, we might be on the verge of discovering living cultures that have maintained continuous existence since their planet's habitable period. Recent detection of seasonal methane variations in Mars' atmosphere has fueled speculation about contemporary biological activity. While geological processes can produce methane, the observed patterns are more consistent with biological sources. If Mars still hosts living organisms, they might represent evolutionary descendants of ancient life forms that survived their planet's environmental transformation. Such organisms could carry within their genetics and biochemistry information about Mars' biological history. If ancient Martian civilizations existed, traces of their technological activities might persist not just in geological formations, but in the genomes of species that have maintained evolutionary continuity since the planet's habitable era. This possibility transforms the search for ancient Martian intelligence from purely archaeological investigation to active biological exploration. Future missions designed to search for contemporary life on Mars might simultaneously uncover evidence of ancient technological civilizations through the study of surviving organisms that preserve information about their predecessors. The implications extend even further when we consider that advanced Martian civilizations might have achieved interplanetary travel during their planet's habitable period. If they developed spacefaring capabilities, they would have had millions of years to establish colonies throughout the solar system. Evidence of their presence might exist not just on Mars, but on asteroids, moons, or even on Earth itself. Some researchers have seriously proposed searching for such evidence in locations where it might be better preserved than on planetary surfaces. The far side of the Moon, protected from Earth's geological activity and atmospheric weathering, could preserve structures or artifacts for billions of years. Ancient mining operations in the asteroid belt might leave detectable modifications to the composition or orbital characteristics of specific objects. Even Earth itself might harbour traces of ancient Martian visitation. If panspermia processes enabled the exchange of living organisms between Mars and Earth, they might also have facilitated the transfer of technological artifacts or information. Unusual geological formations, unexplained isotopic anomalies, or even genetic sequences in terrestrial organisms might preserve evidence of ancient contact between Martian and Earth civilizations. These speculative possibilities highlight how the investigation of ancient Martian civilizations connects to broader questions about the prevalence and longevity of intelligence throughout the universe. We're not just asking whether Mars once hosted technological societies, but whether such societies naturally emerge from biological evolution and whether they can survive and spread across cosmic distances. The answers will profoundly influence how we think about humanity's place in the cosmic order. If we discover that technological intelligence has emerged multiple times in our solar system alone, it would suggest that consciousness might be a common feature of planetary evolution wherever conditions remain suitable for sufficient periods. Conversely, if we find that Mars remained lifeless despite billions of years of potentially habitable conditions, it would indicate that the emergence of intelligence might be extraordinarily rare. Such a discovery would place enormous responsibility on our species to preserve and spread consciousness throughout the galaxy. The investigation continues with each passing day, bringing new data, new analytical techniques, and new theoretical frameworks for understanding what we might discover. Advanced rovers continue their systematic exploration of Martian geology and chemistry. Orbital spacecraft map the planet's surface and subsurface structure with increasing detail. Laboratory analysis of Martian meteorites reveals new information about the planet's ancient environment and chemistry. Future missions will carry even more sophisticated instruments designed specifically to search for techno-signatures and biological evidence. Sample return missions will provide unprecedented opportunities for detailed laboratory analysis using the most sensitive instruments available on Earth. Human exploration of Mars, when it finally occurs, will enable direct investigation of features and formations that robotic missions can only observe from a distance. But perhaps the most important developments will be conceptual rather than technological. As we learn more about how civilizations might interact with their planetary environments and what traces such interactions might leave behind, we're developing new frameworks for recognizing intelligence in the geological and chemical records of other worlds. The search for ancient Martian civilizations represents one of the most ambitious scientific investigations ever undertaken. We're attempting to detect evidence of intelligence across temporal and spatial scales that challenge the limits of human comprehension. Whether we ultimately find proof of vanished technological societies or discover that consciousness emerged only once in our cosmic neighborhood, the investigation itself represents humanity at its most curious and determined. The red planet continues to guard its secrets, but human ingenuity continues advancing toward answers that will echo through our culture for generations to come. In the quiet laboratories where scientists analyze Martian samples, in the mission control centers where robotic explorers are guided across alien landscapes, and in the observatories where telescopes peer into the depths of space, we're gradually assembling the pieces of one of the greatest puzzles in the history of science. Whether Mars once hosted civilizations that built monuments to rival our greatest achievements, developed technologies that surpass our current capabilities, or achieved forms of consciousness that we can barely imagine, remains unknown. But the very fact that we can seriously investigate such possibilities represents a remarkable moment in human development, when our species has finally developed the tools and knowledge necessary to search for our cosmic neighbours. The implications of this search extend far beyond academic curiosity about another world's history. Understanding whether technological intelligence can emerge, survive, and thrive over cosmic time scales has direct relevance to our own species' future prospects. The lessons we learn from studying Mars' ancient history could prove crucial for ensuring that human civilization successfully navigates the challenges that lie ahead. As Mars rises into night sky, that rust-coloured point of light carries within it the potential answers to some of humanity's most profound questions. Are we alone in developing consciousness and technology? Can intelligent civilizations survive the environmental and technological challenges that seem to threaten their long-term existence? What responsibilities do conscious beings have to preserve and spread intelligence throughout the cosmos. The investigation continues, and with each new discovery, we edge closer to answers that will fundamentally change how we understand our place in a universe that may be far more populated with intelligence, both past and present, than we've ever dared to imagine. Tonight, as we reach the culmination of our investigation into one of the most profound questions ever asked, we must confront the ultimate implications of what we've discovered. The evidence we've examined, the possibilities we've explored, and the scientific principles we've uncovered all converge on a single, inescapable conclusion that should fundamentally change how every human being thinks about our place in the cosmic order. The question isn't whether Mars could have hosted ancient civilizations. Based on everything we now know about the red planet's history, the question is whether it could have avoided hosting them. Think about the timeline we've reconstructed. Mars remained warm, wet, and potentially habitable for periods measured not in thousands or millions of years, but in billions of years. That's 1,000 times longer than complex life has existed on Earth. It's 10,000 times longer than human civilization has endured. Within such vast stretches of time, the emergence of intelligence isn't just possible, it becomes statistically inevitable. On Earth, evolution produced thinking beings in a geological instant once the right conditions emerged. The transition from simple life to complex organisms took roughly 2 billion years. The leap from complex life to intelligence required only a few 100 million more. If Mars enjoyed stable, habitable conditions for even half of its early history, that represents timeframes during which multiple civilizations could have risen, flourished, achieved technological sophistication, and vanished completely. The mathematical probability becomes staggering when you consider it properly. We're not discussing whether one civilization might have emerged on ancient Mars. We're contemplating the possibility that dozens or even hundreds of technological societies could have developed during the planet's habitable epochs, each building upon the ruins of their predecessors, each pushing the boundaries of what intelligence can achieve in a universe that rewards innovation and punishes stagnation. But here's what should make every thinking person pause in wonder and perhaps a little fear. If Mars did host advanced civilizations, their absence from the current archaeological record tells us something terrifying about the nature of deep time and the ultimate fate of technological societies. The answer to whether ancient civilizations once thrived on Mars remains tantalizingly beyond our grasp, suspended between scientific possibility and cosmic mystery. What we've discovered tonight isn't just the story of a distant world, but a mirror reflecting our own deepest questions about intelligence, survival, and the ultimate meaning of consciousness in an ancient universe that may be far stranger and more populated than we ever dared imagine.